So I wanted to remind you that we have the presentations in Calvin Lab on the last day of November at 9:30. And I would like everyone to start start thinking about what topic you're going to present, and to fill out this form here. I placed a link in the lecture notes, which are available online, and I will make sure that I'll also email it to the correct email address to the class. It's tentative. It doesn't have to be the final one. You can change it later, but it's a forcing function. I'd like to ask you to send it to fill it out by Monday, so by early next week.
So we don't have edit access to the spreadsheet. I opened it, and
I know. I know you just sent me a request. I didn't want to open it for edit permissions to everyone, so everyone can view it. But I can handle 14 edit requests, and will give you permissions to edit.
Cool.
So just click on the button for requesting edit permissions, and I'll give you edit permissions. Okay, good. So today's topic continues to be Datalog, and we will continue this even on Thursday. After that, we have a workshop next week, which is basically on Datalog. And you're all invited to participate. Joe Hellerstein will give a talk. Max Wilsley will give a talk. Erich Gredel will give a talk about using semurings in logic. Lots and lots of very interesting talks. I strongly encourage you to attend next week's workshop, much more even than the other workshops, but because it's really on a topic that is very close to what we cover in class. So today we are going to discuss basic Datalog without any extensions, without any negation. There is a lot to say about this. And on Thursday, we will discuss extensions with negation. Then we have 2 more lectures after the workshop. And I'm open to suggestion of what we will cover then. We can continue to talk about iterations in logic, Datalog, and least fixed points in logic. Or I can cover probabilistic databases, which is a topic which I like quite a lot. So I'm hesitating between these 2 topics. Good. So let's start with a quick review of Datalog. Why do we need Datalog? It's because first order logic and the fragments that we care about, like conjunctive queries, unions of conjunctive queries, they cannot express even simple queries. Simple queries like transitive closure or like checking the parity of the cardinality of a relation. Datalog fixes the first problem by extending first order logic with recursion. It actually extends only, I should say, union of conjunctive queries with recursion. It does not fix the second problem. In some sense, fixing the second problem is a long-standing open problem. It's not exactly capturing parity. We know how to do this with the logic, but having a logic that can capture all of p time, that is still open. Okay, so let's review the basics of Datalog. A Datalog program is a set of rules, and each rule is essentially a conjunctive query, which I wrote here, where the head is an atom, and the body is a conjunction of atoms. And we distinguish between atoms that may occur in the head. They are called intentional database predicates, and atoms that do not occur in the head of any rule, and they are called extensional database predicates. So here is a quick reminder. This is the prototypical Datalog program. It computes a transitive closure of an edge relation E. The first rule says every nodes XY that are connected by an edge are in the transitive closure. The second rule says that every pair of nodes xy is in the transitive closure, if there exists a z such that xz is in the transitive closure and zx is in the transitive closure. Just a second, I want to get my clicker. This is much better. Okay, so the semantics of Datalog is based on the least fixed point. I find this a very important topic and is often neglected in the literature on Datalog and least fixed point logics because they emphasize logic, but I think it's often more beneficial to emphasize the algebraic properties of the order relation. That gives you a quick and very deep insight into the behavior of Datalog. So I'm going to touch on this topic repeatedly, and this is a quick reminder of something we discussed already last time. A partially ordered set is a set P with a partial order, which means reflexive, anti-symmetric, and transitive. And we will always assume that P has a minimal element, denoted bottom. We consider monotone functions, only monotone functions, which map which have the property that if x is less than y, then f of x is less than f of y. And the definition that we went over last time are the following. In an element x is a prefix point of f if f of x is less than x, is a postfix point if f of x is greater than x, and it is a fixed point if it is both a pre and a postfix point if f of x is equal to x. Okay, any questions about this definition? By the way, feel free to unmute yourself. We are very few, so you don't need to keep muted unless there is some background noise. Okay, good. So here is an example, a picture to help you visualize. This is an order set going from lower left to upper right. And the function is here in blue. So it maps 0 to 1, it maps 1 to 1, it maps 2 to 1, 3 to 2, and so on. You can see how the function goes. Question, what are the prefix points? Now here we have a race. Who can unmute yourself and quickly enumerate the prefix points? Remember, the prefix points need to be mapped below that dx. Yes?
1, 2, 3, 7,
1, 2, 3, and 1, 2, 3,
8, 9.
7, 8, 9, but also 6. Yeah. So here they are 1, 2, 3, 6, 7, 8, 9. The postfix points? Well, the ones that are mapped above. So these would be the 0, 1, 4, 5, 6, 7. And the fixed points are exactly the intersection. Okay, so that is a picture. Keep in mind, this example is a little bit misleading because this is a total order. So the function can only map either above x or below x. Wherever it maps is comparable with x. In a partial order, f of x may be incompatible with x. But I found it difficult to construct an interesting example with a partial order. So that's why this example is a total order. Okay. Yes, go ahead.
Fixed point called a prefix point, and not that, like, if something's larger, I expect it to be like after, so I would expect post. So the terminology seems to be inverted.
So you're questioning the terminology. I'm trying to remember. To me, it made sense. Why did it make sense? It's a prefix point because it's kind of yeah, it's too small to be a fixed point. That's how I read it.
So
yeah, you can we can agree or disagree. It's up to you if you like it or you don't like it, but that is the terminology.
It's pre-order, I guess.
Yeah, that's how I read it. It's too small to be a fixed point, so it's pre. It's if it were to grow, if we wait for it to grow, then it's going to be a fixed point. Okay, question. Does any monotone function have a fixed point or a prefix point? And the answer is obviously no. Yes, go ahead.
No, it's fine.
Unfortunately, I can't see you, so I don't see if you're ready to talk. No, it's not the case. Here is a simple one. Just a function from the natural numbers to the natural numbers. It grows and grows forever and never reaches a fixed point, not even a prefix point. Okay, so we don't always have. But here is a property that I mentioned last time. Not many people are aware of this, but I think it's a very, very useful thing to know. If the function has a least prefix point, then it also has a least fixed point, and the two are equal. Okay, I'll let you digest this a little bit. So if I have a least prefix point, then that least prefix point is also a fixed point. Let's prove this. So let z be the least prefix point. So what do we know about z? We know that f of z is less than z. That's the definition of a prefix point. Now, why is this a fixed point? How can we prove that f of z actually is equal to z?
Apply f to both sides?
Sorry?
Apply f to both sides?
I don't understand, Remy. To precise?
So apply f to both sides. So
yes, thank you. Apply f to both sides, indeed. So how do you continue, Remy?
So f is small, so it should also be greater than your 2.
So we obtained that, this is obvious, it follows from monotonicity. But what do we read from this new inequality?
It can't be smaller because that would violate the least assumption. So it must be equal.
Exactly, but you're a step ahead. I just wanted to point out the obvious thing that f of z is also a prefix point. Yeah, the element f of z also has a property that if you apply f to it, then it's below f of z. And then, yes, then you conclude exactly what you said. They have to be equal because z was the least prefix point. So we are actually not completely done. We only proved that least prefix point is also a fixed point. But why is it the least fixed point?
If there were a smaller fixed point, then it wouldn't be the least prefix point.
Exactly, because every fixed point is also a prefix point. The converse is not true. So if there were any other fixed point, not if there were, for any other fixed point, that is also a prefix point. And since z is the least prefix point, that other fixed point must be greater than or equal to z. Okay, cool. By the way, the converse is not true. And I invite you to think about a counterexample. It requires a little bit of thinking. Why is it the case that try to find a poset and a monotone function that has a least fixed point, but does not have a least prefix point? It cannot have a least prefix point because if it had, then they would have been equal. But I'm claiming that the converse fails, so there is no least prefix point. Okay, cool. So the second notion that we need to, in order to define the semantics of Datalog, is the cleanest sequence, which leads us under some condition to the least fixed point, actually to the least prefix point, which is also the least fixed point. So given the function f, the cleanest sequence associated to this function is the following. The first element is bottom, and every new element is a function applied to the previous element. This defines an increasing sequence from bottom to f of bottom to f of bottom and so on. I called it f superscript, but maybe I should have called it x superscript because I'm going to use x later. F makes more sense in order to justify that it's coming from the function f, but this is not a function. It's a sequence. And it starts from bottom and it increases because by monotonicity, we can prove by induction that it increases. The important property of cleanest sequence is this one. If you have any prefix point z, then every element of the cleanest sequence is below z. So as this grows, it will always stay below all the prefix points. This is easy to see. It follows by induction. The first element of cleanest sequence is bottom, so that's below z. And the t+1 element is f of t, which is less than f of z, because by induction, we assume that the t's element is less than z. And this is a prefix point, so this is less than or equal to z. Good. So that begs a question. Can we use cleanest sequence to get to our fixed point, or to our least, actually to our least fixed point, or to the least prefix point? It's always below that least prefix point. What happens if we take the least upper bound? Is this always the least fixed point of f? What do you think? What prevents this quantity from being the least fixed point? It's a pretty vague question. We need some mathematical properties to ensure that this is the least fixed point. And here is what can go wrong. The first thing is this least upper bound might not exist. This is an increasing sequence. In our partially ordered set, we have no guarantee that such an increasing sequence has a least upper bound. So this is something that we need to require. We need to require this increasing sequence to have a least upper bound. The second condition, which is pretty subtle, is that even if the least upper bound exists, it is not clear that that is indeed a fixed point or a prefix point. We do not necessarily have that f of this least upper bound is equal to the least upper bound. This requires some thinking. What can you say about these two quantities? One is always less than the other. Which one is less than which? Is this less than is the left less than the right, or is the left greater than the right? And again, the left is greater than the right. Very good. Can you explain why?
That's just the direction from the sequence on the top. As we apply f, we get a growing set.
Yeah, you usually prove this by stripping out the least upper bound. And it is obvious that f of this stuff on the left is greater than ft for a fixed t. And the reason is because that ft occurs here. So that is already greater than f of t. When you apply f to it, it's going to be greater. It's easy to see that the left is greater than if any given ft. Yeah, if you doubt this, let me know and we can explain it slower. Once we have this, yes, go ahead.
If you push the f on the left-hand side into the least upper bound, that becomes least upper bound over t greater than or equal to 1, right? So that's a smaller set.
It's true. That is a smaller set. But here we use the fact that it increases. So for the least upper bound, it does not matter if we start from 0 or from 1.
I see.
So the way we prove that the left is greater than or equal to the right is by observing that the left is greater than every element ft on the right. This requires a little argument, but it is not hard to see. And since it's greater than every element on the right, it's also greater than the least upper bound. But in general, in complicated mathematical partially ordered sets, the f can have a jump at the very end of this chain, at the least upper bound, and it might be strictly bigger than the least upper bound. So in mathematics, people add various very natural and hopefully mild conditions under which this least upper bound will always exist, or under which f is commutes with this least upper bound. The commutativity here is called omega continuity of f, while the top property follows from omega completeness. But I don't want to go there. For Datalog, we need something much simpler. We get these two properties for free if we observe that we can restrict our partially ordered sets to have finite rank. Let me explain what I mean by this. It's a very useful concept of the rank of a partially ordered set. And I highly recommend this book by Stanley on enumerative combinatorics if you ever need to dig deeper into combinatorics. But for Datalog, it's not necessary. So a chain in a partially ordered set of a chain of rank k is a strictly increasing sequence of k plus 1 elements. So this sequence is called a chain, and its rank is a number of elements plus 1. Actually, no, number of elements minus 1. Yeah, so a chain of rank k is a sequence x0, x1, xr of rank. A chain of rank r is a sequence from 0 to r, which is strictly increasing. The rank of a partially ordered set is the largest k such that there exists a chain of, should say, rank k in P. This is a rank of a partially ordered set. It's the longest strictly increasing sequence that you can build in that set. In general, this can be infinity. If you think about the natural numbers, we can construct sequences of infinite length. But in many cases that we care about, actually in all cases we care about in pure Datalog, the rank is finite. So let's see some examples. Let's take just the Booleans with the order. What is the rank of this set?
1.
It's 1. Beautiful. That's the longest sequence we can construct. What about this? I take a set A and I construct all the subsets. And I order them by inclusion. This is no longer a totally ordered set. This is that complete lattice. Try to think about the complete lattice or the Boolean algebra of the sets of subsets of A. What is the longest sequence that you can construct here? How long is that?
The cardinality of A.
The cardinality of A. Very good. So you see, this is how we get to finite ranks. What about the following? We have two partially ordered sets. They have ranks R1, R2. And I'm going to construct a new partially ordered set by taking the Cartesian product and ordering pairwise. So xy is less than or equal to uv if x is less than u and y is less than v. What is the rank of the Cartesian product as a function of the ranks of P1 and P2?
Is it the sum of the cardinalities?
Perfect. It's the sum of the cardinalities. So the rank is a very natural measure on a partially ordered set, and it commutes well with these operations like products or power sets. Yeah. So let's put this to use. If we have a function f, monotone function f, and the pose set has a finite rank, then the Kleene sequence cannot be longer than R. The Kleene sequence can start increasing strictly, but at some point it will have one equality. Once it has one equality, it's going to have equality forever. And that must happen at or before R, where R is the rank of the pose set. So if the pose set P has finite rank, then the least fixed point of f exists, and it is exactly it is equal to fr, the rth element of the Kleene sequence. So here you might object a little bit. Kleene sequence might stop earlier, and that's still fine if Kleene sequence stops at 2, for example, f3 is equal to f of 2. Nothing prevents you from considering the rest of the sequence, and they're going to be all equal. And it's still true that the least fixed point is, you can get to the least fixed point by expanding the sequence up to the rank of the pose set. But this is a convenient way to have a notation for the least fixed point. It is a Kleene sequence at position R, where R is the rank of the pose set. Any questions about this? It's a simple, yes?
Entropy or like the logarithm in any way, because it seems to have sort of similar like algebraic properties.
It's a rank, the logarithm. You have a good point. I never thought about this. The rank of a product is the sum of the two ranks. It does behave like the logarithm. I don't have any deep answer here. It's a very nice observation. I'm trying to remember what else does Stanley say about the rank, but he doesn't say much. There is, yeah, I shouldn't speculate. I don't know any interesting answer to that connects the rank to logarithm. Okay, so let's move on and look at Datalog. So we want to define the semantics of a Datalog program as a least fixed point, but the least fixed point where? Here is the discussion that leads to the answer to what pose set we need to consider for defining the least fixed point of a Datalog program. We start from an EDB instance, and I'm going to denote that I, capital I. It is an instance that is the input to our Datalog program. And this instance is finite, and I'm going to denote with A the active domain of this instance. This is a collection of all the constants that occur anywhere in the instance I. Now, if R is any relation of RETK, and it occurs in my program as an EDB, but especially as an IDB, then R can only use the constants from the active domain. So R must be a subset of A to the K. In other words, the instance R must be an element of the power set of A to the K. And remember, A to the K has a finite rank. What is the rank of the power set of A to the K? The rank of a power set is a cardinality of the set. And the cardinality of the set is exactly the size of the active domain to the power k. It's still finite. Okay, good. Now, if we have if our program has multiple IDB predicates, and they have RETs like K1, K2, and so on, then an instance of the IDB predicate, and I'm going to denote that with J, not to be confused with the I, with the input database. J is what we are computing. J is going to be an element of the product of the power sets, because it will consist of a relation of RETK1, a second relation of RETK2. So the entire state of the IDB instance is an element of this Cartesian product. So then the Datalog program defines a function which we call the immediate consequence operator, which takes the current state of the IDB predicates, an element of this big Cartesian product, and returns a new state of the immediate consequence operator. The semantics of the Datalog program is simply the least fixed point of this operator, of the immediate consequence operator TP. Yeah, very simple definition. Any questions about the semantics about this slide? Okay, good. So how do we compute it? Well, we essentially compute clean sequence. And this is what is called the naive evaluation algorithm. We start with the IDB instance initialized to the empty set. And then we repeatedly apply the immediate consequence operator to the current state of the IDB instance, compute a new state, and we stop when they are equal. And this sequence is exactly a clean sequence. And the beauty is now we know exactly how many iterations this takes. Actually, I still agree with this formula here because it's not the right one. What is the right formula? What is the longest length of the clean sequence that this operator can generate? If you look at the post set on which it operates. In other words, what is the maximum number of steps after which the naive algorithm must terminate?
Sum of the cardinalities of all relations.
Perfect. The sum of these cardinalities. So the active domain to the power k1 plus the active domain to the power k2 plus and so on. That's exactly what it is. You can also over approximate this. You can take the active domain to the power of the largest RET and then put a big O because the number of IDB relations is fixed. But we have a very good understanding of the number of iterations that the naive algorithm takes. That's a message. Okay, cool. So that was the basics. This is what we did last time, actually. I should have go a little bit faster. It's much harder over Zoom than in person. But let's see. From here on, it's going to get more interesting because we cover new stuff. We have seen transitive closure inside and outside. So I think you are bored of transitive closure. And you might question, can we write something else in Datalog? And it turns out that yes, we can write several interesting things. And let me directly jump into what we can write here. Here is a query that I think it's fun. We have a graph. Its edges are labeled with symbols from the set ABC. There is a starting node called 1 and red. We want to find all the paths. We want to find all nodes reachable from 1 by a path labeled with a sequence that belongs to this regular expression. Here is an example. Here is our starting node 1. The edges are labeled with ABC. And my question is, which nodes are reachable from 1 via a path labeled by such a regular expression? Which is the first such node that you find?
4.
4, but actually there is one even earlier that you should find.
1.
1, exactly. 1, 4, and what else? One more.
6.
6, exactly. 1, 4, and 6. 6 is interesting. It took me a while to design this example. So it's interesting because you have to go around the loop to get to 6. Yeah, you have AAB, it's fine. And then AAC, it's also fine. But you can't go directly from 1 to 6 because AAC is not in this regular expression. The question is, how do we write a Datalog program to retrieve all these sets of nodes, 1, 4, 6? There is a simple systematic way to do this, and that goes through the automaton that recognizes this regular expression. And you can write down a non-deterministic automaton. I found it actually more convenient because I couldn't fit it on the slide to write down the deterministic automaton. It doesn't matter. You write down any automaton that recognizes the language generated by this regular expression. So you see here, S1 is the starting state. After an AAB, we get back to S1, or after an AAC, we get back to S1. Then we write a Datalog program by creating one IDB for every state. So that IDB returns a set of nodes that are reachable from 1 via a path that ends in that state. So Q1 will definitely contain the node 1 because well, there is not much to explain here. Let's look at Q2. What are the nodes in the input graph that are reachable via a path that you can that in the automaton ends up at an S state S2? And the answer is all the nodes Y for which there exists a node X that lands in S1, and there exists one more edge from X to Y, which is labeled A. What about S3? How do we write Q3? Q3 of Y is what?
Q2 of X, and then from X to Y through A. Perfect.
That is Q3. So I hope you get the spirit. It's actually quite straightforward. Notice that in Q1, we also have to add not just 1 itself, but also all the nodes Y that are for which there exists an X in S3 and a node XY that is labeled B. And similarly for Q4, and then again for Q1. And that's it. This is a program that produces the set of nodes reachable from a starting node using a given regular expression. I think this is cool. It also highlights the utility of having multiple IDBs, which is not immediately obvious if you just look at transitive closure. That doesn't require multiple IDBs. But in this example, it's very, they come in very handy. Okay, and then finally, if we really want is the answer that was requested, then we need to return the node in the state Q1. Okay, are we good with this example? Good. The
so
second.
Could you?
Yes.
Could you walk through so the regular expression, you've given an input string and you're going to check if it's in the language?
Sorry, say
So
again.
how do we? So the regular expression problem, or like the an automata problem, is normally like you have this automata or regular expression. You're given a word, and you're gonna decide whether it's in the language expressed by the regular expression, right?
That is not
Like
the
the
problem. That's not the problem that we are solving.
I think you could
We-
do
Ye-
a chain, like a linear graph representing your string, and then see if like where the answers end up, and that's like kind of your substring or something.
So my question is, how can you convert that kind of traditional regex decision problem into a Datalog solution?
Yeah, you put it before a graph, linear graph.
So the traditional decision problem is given a string, an arbitrary word, check if it is in the regular expression.
Yeah.
Yeah, Connor, that's what you're asking. Okay,
Yeah.
so you can make the following connection. Given any node in this graph, and giving any path from one to that node, that path can be very long. It might follow multiple. It might turn around in cycles. So you have a path from one, a given path from one to that node. The question is whether the word that is spelled out by the labels of that path is accepted by the automaton.
Mhm.
If the answer is yes, then you want that node to be reported by the Datalog program.
And so then you'd so like procedurally compute if word is in your your Datalog program produces this list, this infinite list of strings, and you're gonna sort them and check if your input word is in the list.
Exactly. You can imagine computing this infinite list of strings that go from 1 to, let's say, to node 4. If any of them is accepted by the automaton, then you report node 4.
Okay, makes sense. Thanks.
And by the way, this is actually a standard operation that is done by graph query languages like Cypher. I'm not a big fan of Cypher, but yeah, it's a standard abstraction in programming languages. Find all the nodes reachable by a path that satisfies a regular expression.
So when converting from the automaton, do all of the accept states appear as conjunctions in the answer?
I didn't get the last part.
All of the accepting states in the automaton, is that what you would put in the answer? Because you're
Correct.
not trying to make sure that because you're trying to check which ones end up in state S1, right? That's the accept state.
Exactly.
And
That's
so
correct.
if you had multiple accept states in your automaton, you would just have a conjunction of all of those states.
Perfect.
Okay.
Very, very nice.
Yes, sir.
Here it's a little bit confusing because S1 is both an initial state and a terminal state. But you get it. If S4 were my terminal state, then my answer would be S4, or the union of multiple states if I need multiple of them. Okay, the automaton does not need to be deterministic. We never use the fact that it was deterministic. And it doesn't stop with regular expressions. For example, if we really wanted to play with this, we could also write a Datalog program that returns a set of nodes reachable by a path whose labels spell out a word that is in a context-free language. This is a context-free language of the well-formed parentheses. A is opening parentheses, B is closing parentheses. You can have things like A, B, B, but also A, B, A, B. This is a context-free language. It's really not hard to see how to write this in Datalog, but I'm going to go a little bit quicker and let you examine the slides. We really copy the rules from here. Now we have a binary symbol. This gives us a set of pairs of nodes, X, Y, that are reachable that are connected by a path that whose labels belong to this grammar. And how do we read it? Epsilon means that X and X are always in S. The concatenation as S means like a transitive closure. If XZ is in S and ZY is in S, then XY is in S because of this concatenation. And the last production says that XY is in X if we have an edge from X to U and an edge from some V to Y labeled B, and UV are in S. This is a middle S. Really straightforward. What I realized actually thinking about this, you can go beyond this. And I lost this as an exercise, write a Datalog program that finds maybe the set of pairs of nodes that are connected by a path that spells out a language which is not context-free. Yeah, it's an exercise with 2 stars I put here because it requires you to think a little bit out of the box of this particular solution. And I have the solution here, but I'm not going to discuss it. So I'll let you think about this. Example number 2. It's a different paradigm of programming in Datalog. This example is same generation. And it goes as follows. We still have a graph, and 2 nodes, X, Y, are at the same generation if they have a common ancestor Z. And this Z is at the same distance from X as it is from Y. Distance might be a little bit ambiguous here. It means there exists a path from X to Z and a path from Y to Z that have the same length. So I have this example here, find people as the same generation with Fred. And this is my graph here. This is the EDB input graph. Here is Fred. And my question is, who is in the same generation with Fred? An obvious answer is Eve, because Eve and Fred, they have a common parent. Who else is the same generation as Fred? George, exactly. And it's a little bit, it requires a little bit of inspection because Bob is our common ancestor. Bob is at a distance 2 from Fred, and it's also a distance 2 from George. So these are the answers. Oh, by the way, Fred itself, I forgot about this. Fred itself is also an answer. So for reasons I never understood, whenever I show this graph to my students, they laugh. But this is usually not over Zoom. So I don't know what's funny about this graph. Good. So let's write this in Datalog. The first rule, I gave it away. X and X are always in the same generation. But how do we write the recursive rule? Sorry. When how can I create an how can I construct a new pair XY where X and Y are in the same generation? What do you propose?
An edge from Z to X and an edge from Z to Y.
Exactly, but it is not necessarily the same Z, because they do not necessarily have a common parent, but they need to have parents, but perhaps different parents, who in turn are the same generation.
Mm-hmm.
Yeah, so it looks like this. X has a parent U, Y has a parent V, and U and V are as the same generation. Interesting. And then, of course, we compute the answer, which is the set of people at the same generation with Fred. So these are cool, regular expressions and same generation. But I don't know if you objected to this. These two examples that I showed you, they are not that far away from transitive closure. They are actually transitive closure in disguise. Why is that? Think about regular expressions. How can you write regular expression as a transitive closure?
The set of strings instead of the set of, yeah.
I want to go back and put this on the slide. Can you please repeat this?
Like if I have like a set of strings and the transitive closure, or like an edge in that set is if string A goes to string B, if like the extra character in B is admitted by the DFA or something like that. I don't know if this works.
Let me try to be more precise in what the question is. Suppose you have an engine, like an API, that can only compute transitive closure for you. And you are looking at these two graphs, and you have the input graph, and you have the automaton. And you want to find your answer, but all you can do is to ask for the transitive closure. You can construct new graphs if you want, but you can only ask for transitive closure or reachability, and that's all the engine can do. How can we use that engine to compute the answer we are seeking for?
The accepted words are the ones that are reachable, that reach a accept state from the start state.
Sure, but how do we convert this into returning a set of nodes, not a set of words?
When you look at the labeled edge path, like you look at the path that you took, well, I guess that's not in the result.
You like create copies of the graph that have additional edges that represent like which labels are possible.
Exactly. Those copies are actually the Cartesian product. We compute the Cartesian product between the input graph and the automaton.
Oh.
This creates a new graph whose size is a product of the number of nodes in the graph and the number of states in the automaton. And there is an edge from a pair node, state to a new node, new state. There is an edge if and only if there exists an edge both in the graph and in the automaton labeled by the same label.
Isn't the original graph already just an automaton?
Yeah, you can think of the original graph as an automaton. That's a perfect way to think about this.
But then, like, you would also take the product of the. I don't understand why you need to take the Cartesian product of the graph and the left and the right hand side automaton when you can. Yeah, so let's take your view because it's very good. Think about the EDB graph as being an automaton. And the node 4, if you use this as a final state while 1 is the input state, the node 4 corresponds to a set of words, which are all the words that you find on the path, on all possible paths from 1 to 4. Mm-hmm. That set of words is regular, but it has no connection to what we want to compute. What we need to do is to check if the intersection between that regular expression defined by the graph with our regular expression defined by the automaton is non-empty. We need to find if there exists a word leading from 1 to 4 in the data graph that also leads from S1 to S1 in the automaton. This is why we compute the Cartesian product of the graph and the automaton. And then we find all the reachable nodes from the node 1, S1. And we report only those nodes that are of the form some node with a terminal state S1.
I really wish we had a whiteboard for this. I let you think about this, and let me ask you the harder question, which is, how can you solve the same generation using just transitive closure? This is even harder to see. Here you can also construct a new graph, and that graph will be the product of the data graph with itself. So it will have nodes consisting of pairs like Carol and Eve, Carol and David, Carol and Carol, Eve and David, Eve and Alice. And there is an edge from a pair XY to a pair XU if and only if this happens. So there is an edge from XY to UV. If there exists an edge from U to X and then an edge from V to Y. And then in this graph, you simply check for transitive closure, for reachability, sorry. You check for reachability from XX. If you blur your vision a little bit and think about this pair here, the two edge relation, it's being a single edge from UV to XY, then what this says is that if UV is reachable, then XY is also reachable. And the first rule says that every XX is reachable.
So then can we think of it this way? So if we're constrained of using transit closure, we're essentially constraining the Datalog program to only use the transit closure rule for all recursive rules. So any recursive rule have to have the form of SG in head and then SG and then another relation in the body.
Yeah, so this is what happens here. These two Datalog examples that I gave you, and I claimed that they are more interesting than transitive closure, they turn out to be transitive closure in disguise. In the sense that from a theoretical point of view, they do not go beyond what we can already express with transitive closure if we are also allowed to construct things like Cartesian products of graphs. But the last example goes beyond this realm. Transitive closure is in the complexity space and log space. And it turns out that in Datalog, we can solve problems that go beyond n-log space, that are p-time complete. And that is what I want to show you next. And it's an example that we discussed before, I don't remember in which context. It's the and/or accessibility graph. I think it was in the context of functional dependencies. So an and/or graph consists of two kinds of nodes, or nodes and end nodes. And I'm going to consider a slight limitation of and/or graphs where the and or nodes alternate. An or node will have end children, and it can have an unlimited number of end children. While the end nodes, they have or children, but they must have exactly two or children. They can be the same, but I need to have a number one and number two. So I need to have exactly two or children. And this can be represented in a triple, and I'll show you in an example how this works. And the question is, we want to find all the nodes accessible from a node A. And accessible means it's like computing the circuit. So if A is true, then we compute the circuit by saying that an OR node is true if one of its children is true, and an AND node is true if both its children are true. Here is an example. So here is my AND OR graph, and I labeled the nodes with AND and OR. This node is true. So the AND node above is also true because both its children are true. And therefore, the OR node above is also true, because one of its children is true. And therefore, what can we say about and therefore this node is also true because this child here is true. And this node, this end node is also true, and this node is also true. Everything here is true. Everything is true. It's not a very interesting example. But I hope you got the problem. We are starting from a single node, and we want to see what else is true if we define this node to be true. Notice how we represent this graph using a single ternary relation. We only need to have identifiers for the OR nodes. So there will be an identifier A, B, and C. And for each identifier, X, I'm going to list for each of its end children, the children of that end child. So let's start with C. So C has this end child here on the left, and its children are A and B. This is what the first tuple says. But C has a second end child, so this produces a tuple CBC, because this end node has BC, and so on. Notice that A does not occur in the first column just because this OR node has no children, and that's fine. Any questions about this representation? Okay, so the Datalog program to compute this is really simple. Oh, by the way, my answer here is ABC. I cannot return the end nodes because I don't have a name for them. You can modify the program to return the end nodes, but we don't care about this. We only return the OR nodes. And the program is really so simple that I didn't feel the need to dissect it too much. A is in the answer, and an OR node X is in the answer if you can find an end child consisting of its own children Y and Z, such that both Y is in the answer and Z is in the answer. Very straightforward. The significance of this program is that the end OR node end OR graph accessibility problem is no longer in n-log space. It is p-time complete. Well, we don't know if it's not an n-log space, but if n-log space is different from p-time, then this is not an n-log space, which means that Datalog can express, can solve problems that go beyond what transitive closure can give us.
Does this cover exactly the polynomially sized monotone circuits without negation?
I don't know. If Datalog covers all the polynomially sized monotone circuits.
Because this and/or graph, I mean, it looks like exactly a monotone circuit.
These are monotone circuits. This is the evaluation problem of the monotone circuits. I see. So you're not asking whether everything expressible with monotone circuits can be written in Datalog. And actually, the answer is no, because with circuits you can check parity. But there is nothing deep here. It just says that with Datalog we can evaluate circuits. This is what it says. We can evaluate monotone circuits.
Mm-hmm.
It doesn't go in the opposite direction. It doesn't tell us that everything that a circuit can compute, we can also compute in Datalog. That's something I want to discuss on Thursday.
Can we have loops
Cool.
in
Can we have loops in?
circuits?
Like here?
We can? Okay.
Well, in circuits, we cannot have loops, but these are graphs. These are and/or graphs. And we can still define the graph accessibility problem for p-time completeness, we don't need I mean, the problem remains p-time complete, even if the graph is acyclic. And I don't remember if it's a p-time complete, even if the graph is a tree. I believe so, but I don't know. Okay, good. So that was the story I wanted to tell here. That the problem we just saw, alternating graph accessibility problem, is p-time complete, and therefore, as long as n-log space is strictly included in p-time, it means that Datalog can express strictly more than quantitative closure can do. Moreover, we know that the data complexity of a Datalog program is in polynomial time. For every fixed Datalog program, we can compute its answer in polynomial time in the size of the database, which kind of gives us a pretty good connection between Datalog and polynomial time. And we will see on Thursday that actually these two can be equal under if we add order. Still, Datalog is limited by the fact that it can only express monotone queries. We cannot even compute set difference because Datalog, in order to have this elegant least fixed point semantics, forbids any use of non-monotone operators. They need to be added later, and then we need to revisit all the assumptions that we made. Before we add them, and I still have 5 minutes, but I think we should continue for another 10 minutes or so because we started late. I want to highlight the benefits of restricting Datalog to monotone queries and their potential for optimizations. So that's going to be the last topic for today. And I realize you can see here many slides, but I think that we will be able to cover them in a reasonable time. There are at least 3 major benefits that I can think of. One is the ability to do semi-naive evaluation. We already mentioned this last time, but I want to review it. The second is to do asynchronous execution. Same thing, we mentioned this last time, but I want to go a little bit deeper and so we understand exactly what this means. And another potential optimization, which we will not discuss, is called magic set optimization. It's considered to be a very difficult to understand set of optimizations, and I decided it's not worth our time to discuss it. You can always find good text on magic set optimization. So let's discuss semi-naive evaluation. And I want you to leave this discussion with the impression that semi-naive is really, really simple if you set up the framework correctly. Here is a naive evaluation algorithm. It computes a cleaning sequence. At every time t, it computes it starts from the current state of the IDBs, computes a next state at time t plus 1. The semi-naive, what it does, it first computes a difference, computes what is new in the new state that was not there in the previous state, and then unions this difference. It should be clear that these two programs are equivalent simply because we haven't done anything here. We just split this simple step into 2 steps, computed the difference first, and then we added the difference. The benefit of semi-naive becomes obvious only if we compute if we compute this TP, this immediate consequence operator, in an incremental way. So for that, we observe that the current state of the IDB, this GT, is in turn obtained by unioning the previous state with the previous delta. So the current state is a previous state, union the previous delta. And for conjunctive queries and for unions of conjunctive queries, we can compute a new query called the delta query, which is expressed in terms of the previous state and this delta, and it's often much more efficient than computing the entire query. That is what makes the semi-naive evaluation much more efficient. This incremental computation. Yeah, so this is a formula to look at. Let's quickly review this on the transitive closure. This is our transitive closure. I forgot to mention the current state. We replace the current state here by looking at the previous state, but the previous state exists only if t is 1 or larger. For t equals 0, we need to initialize the current state and the current delta. We need to initialize it separately, and delta will be initialized to the immediate consequence operator applied to the empty set. And we just took out from here the first loop. So getting back to the transitive closure, the initialization is as follows. The transitive closure initially is false everywhere, same as saying it's the empty set, while delta is what we obtain by running the body, both bodies on the initial state, which is the empty set, and that gives us delta, the set of the edge relation. So now we repeat the loop for 1 to infinity. What is delta t? Well, it is the incremental query applied to to delta. And since the query is linear, it's going to depend only on delta. So let me just show it directly. So this is going to be the previous delta joined with the edge relation. And we still need to subtract the previous state of the IDB. This is why I negated here. And we just add this to the current state, and this is when we stop. And we stop when delta is the empty set. Any questions about the semi-naive evaluation on this slide? I hope it's super clear. Good. So some discussion. All Datalog systems that I know, they implement the semi-naive evaluation. So Remy, correct me if I'm wrong, but I can't see. I don't think any system implements just a naive evaluation. That would be way too naive. Now, the linear Datalog rules are very easy to incrementalize because you just replace the IDB with delta. If they are nonlinear, it becomes a little bit more tricky. So here is how to think about delta rules for nonlinear rules. Suppose we have a join of 3 relations, A join B join C. A, B, C, we insert some stuff into A, B, C. Think of these as being 3 different IDBs or maybe the same IDB. How do we compute the delta? So the delta is, the result of the join is the previous state, and what is on the next line is the delta, and this has 7 terms because we need to replace every A or B or C with a delta, and this can be done in 7 ways. You see the issue here. We might get an exponential number of queries, which is not fun. The alternative is to mix all tables with new tables. So this goes as follows. So the join of the updated tables is a previous join. And now what we do is we start by joining delta A with B and C. But then we add delta B joined with C, but also with the entire new state of A. And then we continue by joining delta C with the entire new state of A and the entire new state of B. So the advantage now is that we only have as many queries to compute as many tables we had in the join, much fewer. The disadvantage is that it's often the case in data logs that the deltas can be pretty big. We have no control over the delta. They can be small, but they can also be huge. So we might end up having to use the red relations here might be much larger than the old ones. Okay, so that's all I wanted to say about the semi-naive evaluation. Let's briefly discuss asynchronous execution. And this will take me 5 minutes and then we are done. So both the naive and the semi-naive evaluation is synchronous. By this, I mean that it applies all the rules to all the tuples at each step. And early on, when we started to discuss Datalog last week, some of you, I don't remember who, already pointed out that we could actually evaluate them out of order. We could evaluate the first rule and then evaluate the second rule on the result of the first rule. That would be asynchronous execution. And we can generalize this. We can apply any rules we want on any tuples and repeat this as long as we have a fair computation. And if we have a fair computation, then we should be guaranteed to reach a fixed point. All this discussion works if the Datalog program is monotone. And I want to discuss the underlying mathematical property that makes this work. And the analysis works beautifully if you start from the absolute simplest case. We only have two partially ordered sets, and they have finite ranks because this is how the restriction that we can always make. And now we want to compute the least fixed point of a pair of functions. The first function takes an x and y from the two sets and returns an element in the first poset. And the second function returns an element in the second poset. So the least fixed point of fg is a pair of values xy, such that f applied to xy and g applied to xy returns the same pair xy. Yeah, this is a goal. We want to compute this least fixed point. So we know how to do it. We can compute Kleene sequence. And Kleene sequence looks like this. We start from bottom, and then at each step, we apply the function, and the function is a pair, fg. So we need to apply f to xy, and we need to apply g to xy to get the new state xt plus 1, yd plus 1. So I'd like to call that each step of Kleene sequence is an fg step because we applied both f and g. An asynchronous sequence is any sequence that looks like this. Start from bottom, and then at each step, you have one of three choices. You can either apply both f and g, like in Kleene sequence, or you can apply just f, or you can apply just g, and keep the other component unchanged. So an asynchronous sequence has at each step, performs at each step either an fg step, or an f step, or a g step. That is an asynchronous sequence. The intuition is that an asynchronous sequence also leads us to a fixed point. But let's make that intuition precise. The first observation is that for every prefix point of fg, the asynchronous sequence is below that prefix point. This is similar to the statement with the property that we proved that the Kleene sequence is always below any prefix point. The same applies to any asynchronous sequence. And here is how to think about the asynchronous sequence. The Kleene sequence goes diagonally. It applies f and g. So it at each step moves one left, one right, and one up. One step left, right, and one step up. The asynchronous sequence either applies a G step or an F step or a G step. It can also apply a diagonal step, but it has more options in which direction to go. But it's easy to prove that this asynchronous sequence, by induction, we can prove it that it's always below any prefix point. So fairness, somebody mentioned fairness last time. Fairness, we can define it as follows. We require that for every k, there should exist larger steps m and n, such that m is an f step or an fg step, while n is a g or an fg step. So if I look at this point here in the asynchronous sequence, I want to make sure that there is a g coming up later. And sure enough, there is a g coming up later. And I also want to make sure there is an f coming up later, and there is an f coming up later. And if the sequence is fair, then we can prove that that asynchronous sequence will eventually reach the least fixed point. And again, the proof is pretty straightforward. All we need to prove is that the asynchronous sequence eventually takes over any element of the Kleene sequence. Yeah, so for example, this point here is above what we had on the left. Okay, so I'm not going to go over the proof, but I'd like you to contemplate this picture here. The Kleene sequence goes diagonally. It applies f and g at each moment, and we know that it eventually will reach the least fixed point. The asynchronous sequence is not clear how it relates to the Kleene sequence. It's not clear that if you make, one thing that you should not be misled by is if you go one step up and one step right, you do not reach the FG step. If you apply only G first and then apply only F, you will be below where you, below or above? Above. I think you're right. I think you'll be above where you would be if you apply FG together. This is true?
Below,
yeah, I think below.
The S there, and you get to below. I don't know.
I think you're above. Because if you apply G, the second component is the same as in the FG.
All right, yeah.
But now when you apply F is going to be a little bit higher because it has a bigger first argument. So it's not as easy as saying that these two will meet. They will not meet, but there is this intricate interlocking step between them that guarantees that the asynchronous sequence still converges to a fixed point. Yeah, and this slide is all you need to get the math right. And it's so simple that you can actually encourage you to revisit it in your head and make sure that you can always reconstruct it. Okay, good, cool. Now, how fast would an asynchronous sequence converge? So Kleene sequence, we know converges in rank P1 plus rank P2 time, number of steps. But the asynchronous sequence is not clear. It may take longer. It may take a number of steps, which is the product of the two ranks. I don't fully know this, but it seems intuitive that it might take a much longer step. It turns out you could use the same argument or a similar one to prove that you actually can unnest nested recursion. Oh boy, now I'm looking at it. It's so hard to read. This is a very simple statement here. It says that we are computing the least fixed point of f and g by computing the least fixed point of g for every fixed x. So we will compute the least fixed point of g for every fixed x. And then we use this in an outer loop to compute the least fixed point of x where the inner loop computes the least fixed point of G. Yeah, it's like doing a while over X, a for loop for X, and inside a for loop for Y. And there is a second component here because we also need to compute the output of G, so we need to apply again G. If you look at the steps computed by this nested fixed point, they look pretty much like an asynchronous sequence. And you can prove using the same argument as on the previous slide that you can always unnest a nested recursion and linearize it into a single fixed point of a pair of functions.
Dan, do you think we could continue on Thursday? I think we're over time.
We are over time, and I'm also done. So that was yeah. I'm not going to continue with grounding. Let's stop here. I apologize for running over, and we continue on Thursday.
Okay, thank you.
Thanks. Bye bye.